Yeah, so my name is Davis Vaughn. As he said, I come from our studio. I'm a software engineer there. Technically, I'm on the tidy models team. I work a lot with Max Kuhn, and we do things such as like the recipes package or our sample, or he was the one who originally wrote Carrot, and we're just trying to make a more modular rewrite of that. But recently, I had kind of taken an interest in arrays and matrices in R. Kind of historically, I've had a little bit of frustration with them. I used to work in the finance field where we kind of used like either the XTS package or something like that. And I don't know, that stuff's great, and they've written really good infrastructure over there, but I feel like the way that R deals with arrays has just been a little bit like frustrating or inconsistent, and there are some things that I think could be a little bit better based on looking at other languages like Python with numpy and even Julia. So with that, I just want to kind of start with this a little bit bold, and some people may think it's a little bit mean, but kind of statement about array manipulation in R. I generally think it's inconsistent and doesn't follow at least my natural intuition. You might feel differently. You might have been completely used to this stuff by now, but I think that there's a little bit of a better way to do it. So three kind of main points that I have here are that arrays are frustrating to work with. They're difficult to program around, meaning like if you're writing other packages that might have to use some kind of generalized array structure, it's difficult to be able to subset the thing appropriately or kind of make certain assumptions about what the inputs and outputs of each function are going to be. And then finally, I think it's a little bit underpowered. What I mean by this is that if you compare things to other languages like Julia and like numpy, there are certain things that you can do over there that we'll talk about that you really can't actually do in R, and I think it's a little bit limiting. So there are three kind of topics for this talk. The first is on subsetting. The second is on a new concept for the R world called broadcasting. And then the third is on general array manipulation. There are two pieces of kind of terminology that I kind of need you to understand if you're not familiar with arrays. The first is dimensionality. So if you just have a 2D matrix or a 3D array, the dimensionality of that object is 2 for a matrix or 3 for a 3D array. It's just the number of dimensions in that array. The other is just, well, what are dimensions? These are the set of lengths that describe the actual shape of that array. So if your matrix had 2 rows and 5 columns, the dimensions are just 2, 5. Here's just a simple example of exactly that, dimensionality versus dimensions here. Here we've got this like little matrix. Get used to kind of this form of how I've drawn a matrix. This is just what you're going to see a lot throughout this presentation. It has 2 rows and 3 columns. The set of these things make up the dimensions, and then the dimensionality of this object as a whole is just 2. So I'm going to start with subsetting, and we're going to look through kind of a couple examples, building up on like what kind of manipulation you might be trying to do with a matrix or an array, and see what R gives you back, and see if it kind of matches your intuition based on kind of what you see as you go. So let's get started. I have no idea how that got in there. I'm so sorry. So I went to UNC Charlotte, but I don't know, so I apologize. So let's start with this matrix here. This is the one that you just saw on the previous page, and we're just going to call it X. So there won't be much code throughout these slides, but you'll kind of see it as we go. And mainly I'm going to use diagrams, but when you see X, it's just going to be a reference to this matrix. So the first thing I want you to think about is, if you've used R, how do you subset out a couple columns from this matrix? Maybe I want, for example, the first 2 columns. It's pretty simple. It's just kind of a comma to represent everything in the first dimension, all the rows, and then 1:2 to specify out the first 2 columns. You get it back, and it's still a matrix. It's still got this kind of 2-dimensional structure. Everything seems happy. My question is, what happens if you want just 1 column? Like, what is the result here? I mean, obviously, I kind of understand that this gives me my 2D matrix back with 2 columns, but maybe I don't want 2 columns, maybe I just want 1. If you expect the result to be this, you might be smarter than me. This is my representation of a vector in R. This is no longer a matrix anymore. It no longer has 2 dimensions. It has been kind of dropped down to a vector. And what R has basically said is you only wanted one element from that second dimension. You must not really care about that dimension anymore. I'm just going to throw it out the window, and now instead of having 2 dimensions, you only have 1, so my 1D object is the same thing as this vector. That's what you get back. Previously, with the 2-column example, I had 2 things in that second dimension still, so you still need that information so it doesn't get dropped. If you don't want this behavior, you can use this drop equals false argument. And that kind of keeps the matrix structure that you might have kind of expected based on your original intuition. So that seems okay, but you kind of have to know it exists. And if you're trying to program around this stuff, it's a really common error if you don't know whether you're going to accept 1 or 2 or 3 columns from a user to forget this. And then as your code kind of continues along, maybe it expected a matrix and maybe they only put in 1 column, so you ended up with the vector back by mistake and your code crashes. Let's go into a 3-dimensional world for a minute and look at kind of the same examples that we just did. This is Y. Y is my representation of a 3D array. I could try and draw some 3D structure, but I'm not that good at a graphics designer. So this is just kind of Y as a 3D array, how R prints them. What you'll see is this 1 through 6 matrix will be printed first, and it'll have a couple little things on top that tell you you're in the 3rd dimension, and then it'll print the second array, or the second matrix right underneath it. So this kind of outer bounding box is saying you're in the 3rd dimension. What happens if you want to do or select out the first 2 columns of Y? So I want 1 through 8, and I want 3 through 10, and I probably still want it to be in this like 3-dimensional structure. It doesn't seem to be a problem, right? Like I'm selecting 2 things, so I don't really expect any drop equals false behavior to have to come into play here. But based on what I've been working with X, I probably just do comma 1, 2. If you know R well enough, you'll know that you'll get this error, incorrect number of dimensions. This is kind of frustrating, at least to me, because like I know what I did with X. I kind of expect to be able to do the same thing with Y, and then be able to get the results that just like I intuitively expect, which is just those 2 columns. Unfortunately, you kind of have to do something like this. You have to specify, oh, where's my code? That makes me feel like this, sorry. So it's a little frustrating that you have to do something like this. Instead, you have to add this extra column on the backside to fully specify all of the dimensions. What this is saying is that I want all of the rows, which is before that first column, the first 2, or before that first comma, the first 2 columns by saying 1 and 2, and then I add that second comma, and everything after that says I want all of the elements in the 3rd dimension as well. If you had a 4-dimensional array, you'd have to add another comma on the backside to say everything in the 4th dimension. I kind of feel like this is a little bit overkill, and without that comma, I kind of feel like I have the same amount of expressiveness, so I'd rather just say comma 1, 2 to get those first 2 columns back. You could do kind of the same thing that we did with X and say, well, now we know how to get 2 columns. What about 1 column? Based on previous experience so far, you probably expect that we have to use drop equals false at this point to prevent that like dropping dimension behavior. But I still want to go through this example just to show you what you do get back. If you've done this before, you'll know that you actually get a matrix, which is, in my opinion, like also confusing. When I had this with X, I ended up with a vector. Now I end up with a matrix. What's going on? It's still following the same procedure, so in kind of R's world, it's consistent. But to my brain and my own intuition, I didn't really expect this, and that it was a little bit surprising. What R does is, again, say, well, you started with a 3D object. You said you wanted one thing from the second dimension. It doesn't have any more information anymore, so let's just throw out the fact that there was a second dimension. Now you had a first dimension and a third dimension. Those are still left around. They combine to make a two-dimensional object, which is the matrix you get back. That's a lot of words, so I'd rather just use a little bit of like color to show you how that happened. It took these blue squares on the left and put them there, and it took those blue squares and put them there. And that's how you end up with a matrix back instead of your kind of 3D array. Again, I think that's like not exactly what I wanted, so I probably would have used drop equals false if I was trying to program around this thing. The problem here is that if you compare using drop equals false with x to using drop equals false with y, you'll see that you have these extra comma after the 1 comma. That extra floating comma between the 1 and the drop equals false is something that wasn't there before when you were programming around x. And what that means is that if you have code that could take a matrix, it could take a 3D array, it could take a 4D array, you have to programmatically generate these commas to make sure that you can just subset out 1 column. As a new user, you generally don't know how to make these like missing arguments, and it's really not the most intuitive thing. So just to write generic code that selects 1 column without dropping dimensions is a pretty hard thing to do, and a pretty common thing to do, and I'd like to make that a little bit easier. So the confusion here is that subsetting in R, that kind of bracket notation, is not what I'm calling dimensionality stable. If I pass in a 2D object, I don't always get a 2D object back out. If I pass in a 3D array, you saw that it could drop to a 2D matrix. And I think that is not a desirable property. To sum up that kind of subsetting behavior, we can use this table. It's a lot on the screen at once, but I can kind of focus your attention to these kind of first lines. If you look at the first 2 columns, actually, the way this table is set up, is that I'm saying, well, how many columns do you want to subset? Do you want 1 or more than 1 column? And then do you want this kind of drop behavior? Yes or no? What you end up with is like 4 very different ways to actually subset your matrix based on the thing that you want to do. And then if you look across from left to right, when you're going from 2D to 3D, you have that problem where you need that extra comma generated as well. So hopefully you can see that this is like, there's a lot going on here just to do some like subsetting behavior. And I have kind of a proposed syntax that hopefully is a little bit more clear. So this proposed syntax, if you look at the first row, kind of collapses all of this into just comma 1. I want the first column in a matrix. I never want to drop dimensions. Here's just this kind of comma 1 idea. What you also see is that if you do want to drop dimensions, you have to use a separate function. Personally, I believe that, again, the subsetting operator should be something that's dimensionality stable. So if you ever want to drop dimensions, you should have to explicitly ask for that. That means that it should be a different function. But otherwise, it looks, and you subset it with kind of the same behavior. You have that kind of, on the back side of that extract word, that comma 1 is there to specify I want all the rows and then the first column. That will rip out that first column and will always give it back to you as kind of a one-dimensional vector, as opposed to the proposed bracket operator, which never drops dimensions. Does that make sense? Go ahead.
Would you want optionally to be able to include the trailing comma, or you just want to not have it even be an option?
So the trailing comma of like x bracket comma 1 comma, that gets ignored. They are the exact same thing. Because this never drops dimensions, this behavior in the top right actually was an error for your 3D array, and now it actually means something, like, at least to be intuitive. And because there's never any behavior of like dropping dimensions, you don't actually need that extra comma. It doesn't do anything. So I've made it like ignore it, basically. So I wouldn't kind of talk about this without having some kind of implementation behind it. So there's a new package out there. It's on GitHub. It's not currently on CRAN yet because I'm still kind of it's work in progress. But it's called Array. An array is kind of like tibble. It's designed to provide kind of a stricter array class. It lets you do less, but that kind of empowers you to do more because you're more easily able to predict and program around all of the results. You create an array object from a matrix if you want to. You library the array package, and you create your matrix X like we had on the screen, and then you can just call as array on that thing, and it converts it to your array object for you. It doesn't look too much different. In fact, it really uses the same print method under the hood, at least for now, but it's got this nice little header on top telling you, yeah, this is an array object, and it's holding integers. So let's kind of go with round 2 of subsetting here. If we have xRay, which is what we've called that array object, and we want the first column, it just looks like this. If we want the first 2 columns, it looks like comma 1, 2. Hopefully the symmetry kind of there on the top makes sense, and it's more a little bit along the lines of what you kind of intuitively would have expected, rather than that one in the top middle dropping down to a vector. Unfortunately, it's a little cut off, but on the bottom, what you'll see is there's y array, comma 1. It looks exactly the same as the code above it. And then y array, comma 1, 2. Again, looking exactly the same as the code above it. So there's kind of this like top to bottom symmetry as well of, do I have a 2D array, do I have a 3D array, ND array? It doesn't matter. If you want the first column, it's always comma 1. The other function up there was extract. Really in RA, it's called array extract. And it always drops to 1 dimension. So rather than having that behavior of my 3D array dropped to a 2D matrix just because I requested 1 column, so it kind of threw that out, array extract will always rip it out and drop it to a 1-dimensional vector. So if we wanted that first column there, 1 through 8, it rips that guy out and gives it back to you as a vector. Make sense? Any questions? So that is the subsetting section of RA, and I kind of want to move on to the broadcasting piece. I find this one a little bit more interesting. Broadcasting is a new concept for R, but it is well known in the NumPy world. How many of you have ever used like NumPy? How many of you know what broadcasting is? Yeah, cool. So at least some of you will be familiar with this concept. Broadcasting has to do with kind of the 2 definitions we've talked about. It has to do with increasing dimensionality and recycling dimensions. If you're not familiar with what recycling means, imagine having like a matrix with 1 row and you wanted to make that have 3 rows. Recycling is the idea of taking that 1 row and copying it down twice, and that means you've recycled from 1 to 3 rows. It's a fairly simple idea. So let's do some math. I won't push you too hard, but I will make you do a little bit of math today. Here's X. It's a 2x3 matrix. Here's Y. I'm just calling it 1 here. It's a vector just holding 1. Hopefully, you can kind of grasp that the answer should look something like this. 1 through 6. Now we have 2 through 7. We just added 1. The shapes look the same as X. This might be a super simple looking example, but it actually kind of holds all of the concepts of broadcasting that I'm going to want you to learn in this like kind of next 10 minutes or so, just in this one example. What the question I want you to ask yourself has to do with Y. Specifically, the question is, how is Y reshaped or stretched or whatever in such a way that this operation can work? You might have your own kind of intuition about how 1 is added to X and how that happens, but there's this kind of procedure that I want you to follow. And if you do that, you'll have this general understanding of how broadcasting actually works. So here's the first step. we're going to increase dimensionality. If we kind of put the dimensions of x and y in this little table format in the top left corner and left align everything, then what you can see is that y has a dimensionality of 1 and x has a dimensionality of 2. By increasing dimensionality, the way you actually do that is by appending 1s to the dimensions of the lower dimensionality object until it matches the dimensions of the higher dimensionality object. That's a lot of words and a lot of kind of confusing dimensionality stuff, so I've kind of done the picture there on the bottom as well, and hopefully you can see that blue color. What that means is that y has now gone from a dimensionality of 1 to a dimensionality of 2. It's gone from a vector of 1 to kind of a 1 by 1 matrix instead. Anytime you see this blue color, that's going to mean something is new. It's been added by broadcasting. If you want to see what that actually looks like what happens to y whenever this broadcasting procedure is done, at least this first step, it goes from the vector to a matrix. The second step is to take these objects that now have the same dimensionality and do a recycle of their dimensions. So the way you do this is to look vertically down each dimension, now the dimensionalities all match up, and recycle any dimension that is length 1 up to the other dimension. So in English, the rows of y had length 1, and the rows of x had length 2. So we take the 1 from y and recycle it to match x. So y is now going to have 2 rows instead of just 1. And that's how we recycle the first dimension. So at the bottom there, you'll see that the 1 in that first dimension for y has changed to a 2, and it's become blue. Something new has happened. Again, if you want to kind of see what happens, that means that the 1 by 1 matrix is kind of copied downward, and we get this second row for y. It's blue because it's kind of like a virtual thing. It hasn't really changed. We're just kind of thinking of it that way. We need to do this for the columns as well. So if you look at, again, y is the one that needs to change here. It has 1 column. X has 3 columns. We need to recycle the columns of y from 1 to 3. And if you look there, y has a 3 at the bottom instead of a 1. What this has also allowed us to do is determine the final dimensions of kind of the output object. So if you now look up and down, x and y both have 2 rows, well, our output probably has 2 rows. X and y have 3 columns, well, our output probably has 3 columns. So if you want to see what happened to y, it has gone from having 1 column to having those columns recycled kind of to the right there, and now you have 3 of them. You'll immediately notice x and y now have the exact same shape, so you can add them together pretty intuitively. 1 is out of the 1, 3 is out of the 1, 5 out of the 1, and so on. So you get the result that we kind of intuitively knew at the very beginning. So I want to kind of back up for a second and say, well, what if we started here and gave R this instead? This is our 2 by 3 matrix that we started with, but now instead of starting with a vector holding 1, we start with this 1 by 1 matrix. We're to give R these 2 things. Unfortunately, the result is non-conformable arrays. You get an error back immediately. Now, this was kind of an intermediate step as we were going through that broadcasting procedure. After step 1, when we increased dimensionality, we had this exact problem. So we know that if we finish out the broadcasting steps, then it has an answer, at least in terms of the broadcasting rules. But for R, and its kind of interpretation of how arrays should be added together, it doesn't know what to do here. And again, with parts and rray, that makes me feel like this. I want to do exactly that with my computer. But for every time I hit this error, it makes me really upset. Because I think like I know enough from the numpy world that this should work. Like things should be able to be added together like this. So kind of the one sentence statement is just that R doesn't broadcast. We didn't really get lucky that it worked with scalars. I say that here, but really like that's the design of how R arithmetic works, and it doesn't really work well with matrices of different shapes. But again, we know the result. We know the result looks like 2 through 7, and we know that because if you finish out those broadcasting rules, the 1, 1 matrix here transforms into this 2 by 3 matrix, which can easily be added to X. So at this point, I kind of want to firm up these broadcasting rules a little bit, and then we'll do an example that's a little bit more complicated. The broadcasting rules are at least to me, there's really only 2 of them. And again, it has to do with that dimensionality and dimension stuff that I've been mentioning. The first one is that you match dimensionality by appending ones to the backside of the lower dimensionality object. And the other rule is that you just match dimensions by recycling those of length 1. If you do those 2 things, then you'll be able to recycle or broadcast objects into shapes that can be added together, which means that you do things that you couldn't do before in R, which hopefully means that we've opened up the door for a lot more powerful operations. Again, I wouldn't tell you about this if there wasn't some implementation behind it, and RA does broadcasting. Here's the same example we've kind of been looking at. If you have X, 1 through 6, Z is my representation here of that 1 by 1 matrix. Add X and Z together in R and you get non-conformable arrays. Transform either one of them into an RA, and immediately you get broadcasting. Add them together, and we get our 2 through 7 result there at the bottom. Any questions on that so far? So how does this work? Well, really, all hail our C++ overlords, because these people at QuantStack have kind of taken the idea of numpy and transformed it into something they call xtensor. Xtensor is a C++ header-only library that implements all of the numpy features of broadcasting and a lot of the numpy kind of manipulation functions for matrices and arrays, but have done it in C++, so I could then bind to that and give it an R interface on top. Because of that, it's very fast, and it's a very well done library. So let's give a more complicated example of broadcasting. Let's go 3D again. Here, X is just this 1 by 3 by 2, 1 row, 3 columns, and kind of 2 deep, if you will, 3D array. Y is 3 by 1. I mean, the first question is like, I'm in the R world. Can I even add these things together? And immediately, obviously, like R will give you the non-conformable array error. But with broadcasting, you can actually add these things together, and they do actually have a meaningful answer. Let's go through our steps. The first step is to increase dimensionality. Put things on our table like we had before. X and Y together. Y has dimensionality of 2. X has 3. So Y needs to have the ones appended to it. That's what you see with blue down at the bottom. What changes in our diagram is that Y now gets this blue box around it saying, okay, now I'm in the 3rd dimension. Now that the dimensionalities match, we need to match the actual dimensions, and that means we need to do some recycling. If we look through how we got from kind of A to B step by step, we go through each column. So we'll look at the rows first. In this case, X is the one that has to change. It had 1 row, it needs 3. So that's why you see a 3 on the top right. For Y, the columns need to change. It goes from 1 to 3. And then for Y, also something we haven't seen yet, the kind of 3rd dimension has to change too. Instead of just having 1 element in the 3rd dimension, we need 2. So if you're kind of like wondering, how do I even picture how things are like reshaped, hopefully this helps a little bit. So this is the reshaped X and reshaped Y. What you'll see with X is that we had 1 row And now that one row has been copied down twice for both kind of pieces here. For y, we had one column. We needed 3 columns, so that has been copied over twice. And then we went from 1 element in the 3rd dimension to 2. So we took the entire matrix and copied it down. Make sense how that reshaping kind of happens? So now, again, you've done your increasing of dimensionality, you've done your recycling, you have 2 things that can kind of intuitively be added together, and you get this result. You might be wondering, like, why would this ever be useful? But beyond it being kind of a cool operation, it's actually the outer sum of 1, 2, 3, 1, 2, 3, and 4, 5, 6, 1, 2, 3. And then you get the outer sum back in this cool 3D array format. Rather than having some special function that does outer sum is just kind of a mixture of addition and broadcasting in the NumPy world at least. And now it can be in R as well. Any questions on broadcasting? Cool. So I talked about broadcasting to get up to this point because with the manipulation section, I want to use it and kind of show how broadcasting can be useful, at least for some kind of like more data analysis type stuff that you could do with matrices and arrays. The main thing when you think about array is to not just be this like fancy new array that does broadcasting and can like subset a fancy way. I want it to be more general than that. It really should be a toolkit, kind of a toolkit that has a lot of functions inside of it that are useful for actually manipulating your array in one form or another. There will be functions to actually do explicit broadcasting if you want to, rather than just have it being done implicitly. There will be functions for detecting duplicates, functions for splitting an array in multiple pieces. But the best part is that it all still works with base R. It doesn't mean you have to opt in to always using these array objects. If you want to use any of these functions, they're all available to you to use with matrices, to use with arrays, to use with vectors. They all work with any of those. They also just happen to work with array objects as well. Now, if you want that special subsetting behavior, you could either call, it's not shown on the screen here, rray_subset on a base R matrix, and that will like kind of automatically promote that matrix to have that behavior. Or you could go ahead and kind of change your matrix into an array object, and then that like bracket notation gets you that special subsetting automatically. What I can't do, obviously, is override base R's subsetting operator for matrices, and nobody wants that anyways. Go ahead.
Do the array objects inherit the underlying array class?
They don't. That was
like tibble.
That was the way I started, and unfortunately, I think it's going to break too much code if I do that. Because people are going to think like, well, I can just like insert it into this old code that I used to have, and it should like work the same automatically. And it will 99% of the time, but that 1% of the time where like your old code expected an error and now something broadcast is what I'm kind of afraid of. So that's why it doesn't. So there's a lot of functions on the screen here, obviously, and there's a lot more that that is for. But the one I want to focus on right now is rray_bind. This is kind of the RA enhanced version of cbind and rbind from base R. So if you look at these two matrix objects and just kind of quickly ask yourself, how can we like bind these two things together? This isn't like an addition, this isn't multiplication or anything. I'm just saying, what if I want to like stack 1 through 2 and 3 through 4 like on top of each other, like a row bind, or maybe like left and right, like a column bind? Well, it seems like there might be some like gaps if you try to shove these two things together. So how does base R handle this? Well, if you want to do a cbind with these two objects, unfortunately, you immediately get an error. Number of rows of matrices must match. And this isn't like too surprising. You know, I want to column bind 1 through 2 and 3 through 4. Well, I probably have to have the same number of rows in both things, so everything like all the pieces line up the right way. Similarly, if you do an rbind with these two objects, like putting one on top of the other, you'll get an error. Number of columns must match. It's kind of the same idea. Luckily, we know about broadcasting, so we know we might be able to kind of manipulate these shapes in some certain way that they actually can be like bound together in a nice form. And rray bind kind of lets you do that. If we specify that we want to bind these two things together and say that we're wanting to bind along the first axis, this is kind of the same thing as an rbind. It takes 1, 2, puts 3, 4 on the bottom of it, but then says, oh, I needed to fill stuff in along the way. So it fills in 1 through 2 and kind of broadcasts it across the columns. It's kind of a partial broadcast. It does the same thing as what a normal broadcasting procedure does, but when it's actually performing the broadcast, it leaves out the axis of interest. So it broadcasts the columns. This is a 3D object. It would also broadcast kind of the depth of the third dimension, but it would never try and broadcast the rows if that's what you're trying to bind together. Yeah.
Quick question.
Yeah.
I'm not super familiar with the broadcasting, but I could imagine there might be a circumstance where I don't duplicate the values, but I might want to fill it with something else, like say zeros.
Yeah.
Is that something that's supported or possible? Is that just antithetical to what broadcasting is supposed to do?
I think it is antithetical of what broadcasting is trying to do, because it does mean that you're kind of like duplicating that out so you can add the shapes together. But it's not, there's nothing to say that you couldn't create like a matrix of all zeros and then bind those together. So yeah, like it's possible. And it's not like a bad thing, yeah. So you could switch this and say, well, maybe I wanted to bind along the columns. Maybe I wanted to do like a cbind instead. So axis equals 2 means that like you take 1 through 2, you stick 3 through 4 up there on top where the 1 is, but obviously you need to fill some gaps as well. So it broadcasts down the rows. You could do something even crazier and say, well, I want to broadcast along the third dimension, and this might like not intuitively make any sense if you're really not familiar with broadcasting, but all it means is that we broadcast the shapes of the first and second dimension and then stick these two matrices together in the third dimension. So the columns of 1 through 2 need an extra 1, and the rows of 3 through 4 need an extra 1. Now you have two 2x2 matrices that you can kind of stick together into the third dimension. And once you really learn about broadcasting and get familiar with those two kind of steps that I talked about, that's the rules that this is using behind the scenes. So it's all very consistent, and once you learn it once, it applies to everything else in the package. The other function that I wanted to talk about has a bit more of a data analysis feel, at least my example does, and it's rray max. So as a quick thought experiment, what would you do with R code if you had X here, this matrix, and you wanted to kind of normalize it by dividing by just the maximum value in the matrix? In this case, that would be 6, so I want to divide all the elements by 6. What if you also wanted to do that kind of along the columns? By that, I mean you actually look at each row, take the maximum value in each row, and divide each row by that maximum value. So you take the first row and divide by 5, the second row and divide by 6, and then you want to do it along the rows, which actually means that you take the first column and divide by 2. It's a little bit kind of a confusing language at the beginning. And then the second column is divided by 4, and the third column is divided by 6. How would you do that with some R code? After thinking about it for a little bit, you might come up with something that looks like this. If you have never used Sweep before, congratulations, you are probably under 25. So a lot of times we don't really use the sweep and apply functions too much anymore because we use data frames now, and we're used to how dplyr can manipulate things. But if you do use a lot of base R and you use a lot of matrices and arrays, then you have seen this sweep apply combination before. What we can do to get our kind of global maximum value of X is just X divided by max X. Max of X just returns a vector back to you, and it just gives you 6, and then you're able to do that kind of X divided by 6, and it does all the right things. To do a bit more complicated stuff like row-wise and column-wise division, you actually have to use this ugly sweep apply code that I'm not even going to try to explain. For some people, this might, again, make a lot of sense. You might be really familiar with the idea of like sweeping out a statistic. But for me, I just like feel like there's some inconsistencies of going from x divided by max x, and why can't I just do like x divided by max x row-wise, x divided by max x column-wise? So that's what RA max allows you to do. It lets you, for the global version, not specify any axes, and it just takes the maximum value, which is 6. X divided by 6 lets you get the result you expect. But then if you want to do it row-wise, or you want to do it along the columns, you specify axis equals 2. And you want to do it along the rows, you specify axis equals 1. And this is the exact same kind of answers that we got before, but hopefully with code that's a little bit more intuitive for what you were trying to do. And if you wanted to switch from row-wise to column-wise, it's just changing the axes. The last thing that I kind of want to do here is demonstrate how broadcasting and the kind of RA max work together to let you do the result at the bottom. So if we take a look at just what RA max gives you back, and we wanted to do it along the rows, 1 and 2, well the maximum is 2, 3 and 4, well the maximum is 4, 5 and 6, well the maximum is 6. RA max is dimensionality stable. If you gave it a 2D object, you will always get a 2D object back. Some people might say, well I could just get a vector back, 2, 4, 6, and that would be okay, but it doesn't broadcast well against the result. So just bear with me that I think this is a good idea. You get a 2D object as an input, you'll get a 2D object as an output. You could take 2, 4, 6 then, which is the result of RA max, and say x, our matrix, divided by 2, 4, 6. What that means is that then 2, 4, 6 has to be broadcast down to have that second row. Now, 1 through 6 can be divided by this 2, 4, 6, 2, 4, 6 matrix. That makes intuitive sense of what the result should be. It should all be done element-wise at this point, and you kind of get the result that you intuitively want. Any questions on how that works? Yes?
There is like a p-max, like parallel max function in R, but I forget, like, that doesn't do this.
Yeah, no, it's like multiple objects that you could, like it could be x and y, that you could take parallel maxes between. So, yeah. Good question. So to finish up, I kind of started this talk by saying that, to me at least, base R arrays are a little bit frustrating to work with. I think they're kind of difficult to program around when you're making new R packages. And then compared to things like NumPy and things like Julia that have broadcasting kind of deeply baked in, I think they're a bit underpowered because the sweep apply things that you have to do to get the behavior you wanted intuitively just seems a little bit like more code. So I kind of want to leave you with the idea that hopefully arrays can be intuitive to work with. Hopefully they can be more predictable to program around with RA. And hopefully with broadcasting, they can be much more powerful. That's all I have. Here's some links to my GitHub, to the GitHub and the website if you want to check it out. But thank you very much.
Got time for lots of questions?
Yeah, we're going to plenty of time for questions. Sure.
So does this package have some similar function to Python like reshape? If you get it like the extra kind of reshape.
Yeah, there is like literally RA_reshape, and that does exactly what like kind of the NumPy version would do. If you had a 2x2 matrix and you wanted it to be a 4x1 matrix, since it has the same number of elements, you can reshape that to do exactly that. Yeah, you can give it x and then comma, 4x1, and it will reshape that thing as you might expect. Yes?
In terms of the broadcasting, is there, I'm thinking about a pretty extreme edge case, but like, is there a performance penalty where it is literally say, taking that smaller matrix or smaller vector, broadcasting it by duplicating it. And
Yeah.
you're now creating a much larger object than you might have had originally, versus if you were a little, like under the same, you obviously clever, you could just iterate over
Yeah.
and not have to create that larger object.
It's a great question. Yeah, the question is basically like, when you're broadcasting and you have like broadcasted those columns, did you actually like pay a performance cost by duplicating those columns or memory cost? The answer is no. Xtensor is much smarter than that, and so is numpy, and that they'll just iterate across it the right way. So it's kind of like repeatedly iterating across the same thing. You never actually materialize those extra columns. That's kind of the idea of anything you saw in blue up there as I was broadcasting is virtual, and it's never actually materialized. You never pay that cost. It's a great question. Anybody else? Yes.
So are there any immediate opportunities that you see to use this like underneath other packages? Like one thing that's interesting